Okay, well, I think we will go ahead and get started, and I'm sure more folks will join as we get going. So it is my pleasure to welcome Dr. Camilla Danielski. Uh, Camilla attained her PhD in 2014 at the University College London in the UK, working on the optimal extraction of planetary atmospheric signal out of astrophysical noise. She has been participating in several international projects and collaborations such as Gaia, JWST-ERS, and GTO, LISA, that we'll hear about today, and the Ariel Consortium. Since 2018, Camilla is the leader of the Stellar Characterization Working Group of the Ariel Consortium. And since 2019, she is the scientific leader of the interdisciplinary team within LISA, Astrophysical Working Group, which works on the development of the science case on planetary detection with gravitational waves. And she is currently a researcher at the Institute of Astrophysics in Granada, Spain. So Dr. Danielski, I will turn it over to you, and thank you again for speaking with us today.
Thanks, Joe. So I'm really excited to have this opportunity to tell you a bit more about this new observational window, which is using gravitational waves to detect exoplanets everywhere in the Milky Way and also in the Large Magellanic Cloud. I want to take like 1 minute to acknowledge all of my collaborators, because this is clearly an interdisciplinary group effort, in the sense that we have exoplanetary people, we have double white dwarfs people, and we have gravitational wave experts. And all of us, we are working to develop this science case, which is, well, in the framework of the LISA adoption. This happening in this year, by the end of the year. Okay, so let's start. So LISA, it's the Laser Interferometer Space Antenna mission. It's a large mission, L3, by the European Space Agency. It's composed by 3 spacecraft orbiting the Sun. And more or less, they have like a triangular configuration with 2.5 million kilometers, and they have 3 arms of a laser interferometer. The advantage of LISA is that obviously, being from space, you can go through a completely different frequency range, and for such, it's going to cover a range between 0.1 millihertz up to 1 hertz. Which is a much richer frequency range than the one we can reach from Earth with LIGO and Virgo. You will see after in the next slide that we'll have many more sources in this frequency range. So as I mentioned, the adoption is by the end of 2023. We are working on the Red Book, and the launch will be between 2034 and 2037. So this is like the hold on a second, I can't see my cursor. Can you see it? Right, I don't know, it's not appearing anymore. We tested before. Okay. So in the frequency range of LISA, the bulk of the population is basically double white dwarfs. So all of you see like the purple data points that you see on the left. Those are all compact double white dwarfs, and the triangles are the verification binary that will be used to indeed test LISA as soon as it's gonna fly. Studies mentioned that like LISA will detect tens of thousands of double white dwarfs that are detached everywhere in the Milky Way. So on the right, you have the bulk of the population that is basically double white dwarfs that have a period of around 15 minutes. So between the frequency range of LISA, we can detect every galactic binary that has like between 3 minutes and 30 minutes of period. The fact is that like we can detect it because compact white dwarfs emit gravitational wave at millihertz frequencies. And given that their orbit is slowly shrinking, it's producing like a monochromatic gravitational wave, which can be detected by LISA. But what are double white dwarfs? So they are composed by 2 white dwarfs. They are very peculiar stars in the sense that they have the size of the Earth. but still the mass of the sun, like they can reach maximum like 1.4 solar masses. They have progenitors of less than 8 solar masses, but this is different, of course, for a compact double white dwarf evolution because the masses go lower. They are intrinsically faint, so 10 to the 4 fainter than their progenitors. What is very interesting is being like a cold dead star is because their radiation is cooling down, and so the radiation reddens. They start very hot, up to more than 30,000 Kelvin, and then they cool down to 2,000 Kelvin until it completely like black out and becomes black dwarfs. Again, being with the fact that they are cooling down, they have also a close-in habitable zone, meaning that as the star is cooling down, the habitable zone is going to get closer to the star. They are natural clocks for which we can get like precise age from the luminosity, something that is not possible with main sequence stars. And they are photometric stable to better than 1% if observed in 1 hour to 10 days. What is very interesting is that like 90% of the stars in the Milky Way will become a white dwarf. And again, because of if we observe these stars and we find planets around these stars, we have finally a window to observe the final fate of exoplanets. Most of the study of exoplanets, as you might know, they're focused on main sequence stars, or you might have like very young exoplanetary systems, but like few planetary systems have been detected that are that old, like orbiting white dwarfs. So the more we detect it, the more we can get to pin down the evolution of planetary system after the star gets off the main sequence. So how does it work? How can we detect an exoplanet through gravitational waves? Right, so as I mentioned before, the double white dwarf itself, when it's compact, is emitting a gravitational wave. But in the moment that we include like a third object, such as a perturber, we will have that this perturber will change the center of mass of the double white dwarf, which will move on a Keplerian orbit. So, as I said before, it's a monochromatic gravitational wave. For such, like we can assume that it's constant because the frequency of the gravitational wave is changing on timescales that are much larger than the observational timescale. So what will happen is that we will see the modulation of the gravitational wave emitted by the double white dwarfs, but with this perturber. In a very simple word, we can just approximate this to the radio at hand. For such, we have a carrier, which is our double white dwarf in the center. And then we have a planet. And so a third body, it can be anything. It can be a star. Like the larger it is, the better it is, which will cause a perturbation. For such, like what we obtain in the end, it's a modulated result, which is periodic. And from this periodic modulation, if LISA observes it, we can determine 3 parameters from this signal, such as the planetary period, the orbital phase, and the radial velocity semi-amplitude, as well as the eccentricity. But the eccentricity is a more tricky case. So these planets that are orbiting double white dwarfs, we call them Magrathea. For any of you that is like love the book of the Hitchhiker's Guide to the Galaxy, because in the book it says that Magrathea is a planet that is orbiting 2 white suns, and for such, obviously, it would be like a double white dwarf. So we call them like Magrathea exoplanets. Okay, so we can detect them, but like, what's the advantage of using gravitational waves? Well, the main advantage is that we do not rely on the light, and so we can detect it everywhere in the galaxy. So how did we do? We simulated, we used a simulation of a galaxy double white dwarf population. We injected circumbinary substellar bodies, such as both in the range of exoplanets and brown dwarfs. And then we tested like how many exoplanets or brown dwarfs LISA could detect. For doing such, initially we used information matrix analysis, and we assumed only one planet in a circular orbit because as you will see, it's already like quite complicated to use one planet. Just imagine like more than 3 bodies in the system. Okay, so the injection of the circumbinary substellar bodies was done using different priors to try to understand indeed if there was any change in the detection. And the optimistic case you see here on the left, the first panel, where all of the red triangles are the circumbinary exoplanets that we can detect with the gravitational waves. The green dots are the brown dwarfs. And you will see obviously that like brown dwarfs are much more detectable. Why so? Because of course, like if you have an object that is more massive, it's gonna perturb like the center of mass of the binary much more. And then I put like a zoom on the solar neighborhood, which you have the sun at the center of the 2 lines, and all the known exoplanets that we have detected up till now with the electromagnetic observation. So you see the transits that are the blue triangles, and the Kepler field, which is the one that is go further out because it was a longer observation. In average, we have that with electromagnetic observation, we can just observe with the main techniques up to 3 kiloparsec. We can get to 8 kiloparsec with microlensing, but just, which are the blue triangles, but just towards the galactic center where we have a crowded field, and for such the probability of having a microlensing event is much higher. So this was the optimistic case, but it's really good to see that even in the intermediate and the pessimistic case, we are able to detect exoplanets that are far away from our solar neighborhood. And this is a very important thing in the sense that we are currently just observing the solar neighborhood, and we are assuming that in the whole galaxy, the population is like the one we see. But we don't have any detection outside of the solar neighborhood, and having new constraints on other kind of exoplanets far away, that will be very, very great for developing also the population on a galactic level. We then tested as well, like as a function of the observational time, whether like we could improve the number of detection for both planets and brown dwarfs. And here you see on the left, when we observe for 4 years, which is the nominal mission, nominal time for the mission LISA. And then on the right, if we have an extended mission with 100% duty cycle. You'll see that always the detection, it's like we are able to detect exoplanets that have a period that is less than the observing time, and we can go down. We can go down to smaller exoplanets only if we have a very high signal to noise of the gravitational wave. So sometimes, like on the left, you can see that there's an exoplanet of 1 Jupiter masses, but that's a very lucky case. So I put some numbers on the right just to give you an idea of our results. But this was an injection analysis, so we don't know what is the real population that we will have of exoplanets around double white dwarfs. More on this later. Not only in our galaxy, but also we can detect exoplanets in the Large Magellanic Cloud. So this is obviously a function of the signal to noise of the double white dwarfs, the hosting double white dwarf. So you see here on the left an histogram of the number of detection we could get as a function of the distance from us, from the sun. And specifically in the Large Magellanic Cloud, which is the closest one, where if we observe for 4 years, we are able to detect 70 double white dwarfs. So we use the same process to test the detection for the Large Magellanic Cloud, and we obtained that we can detect exoplanets, but obviously they will need to be more massive because otherwise we're not going to detect the signal. What I showed before, it was specifically an information matrix analysis, but then we decided to go deeper, and we analyzed, we performed a Bayesian analysis, and this time we also included the eccentricity. So this was done in collaboration with the LISA data processing group. So all of these people that you see listed above. And so we tested many different the optimistic population as a result of the previous analysis. And so if we fit for the planet, so we use a gravitational wave waveform where we know that there's a third object. We can have very good results. For instance, here it was a retrieval of 12 Jupiter masses exoplanets. The double white dwarfs had a signal to noise of 89, and the distance was 4.3 kiloparsec. And here you see the posterior of the exoplanet, where you have the true value as the vertical line in blue. The same is for the brown dwarf. Of course, with brown dwarf, as I mentioned before, it's easier. So in this case was 30 Jupiter masses, but the signal to noise, if you might look at the double white dwarfs, it was 883. So that's very useful to constrain in a proper way all of the exoplanet parameters. So here you have exoplanet or brown dwarfs. The posteriors are the amplitude of the signal in order from left to right, and then the phase, and then the eccentricity, and then you have the period, and the last is the time of passage of the periastron. The problem comes when you don't know that there's a third body. So there's you're actually receiving the signal from a three-body system, but then you fit for two-body waveform. And in that case, we have that this is completely offset. You see that the derivative of the frequency of the gravitational wave, which is the most on the left, sorry, it's completely offset. And that means that automatically the binary chip mass will be erroneous, and then you will have a very wrong characterization of the inner binary, because there is a third body that we are not accounting for. So here comes all of the challenges of the data analysis team and for developing the global fit pipeline. More specifically, I just included some posterior observations. So you have on the top row, you have the undetectable systems, and in the bottom row, you have the detectable one. So the blue are just GR only template, and while the orange is when you account for the third body and what you retrieve. Again, the vertical and horizontal lines are the true values. And overall, throughout all of the population, we realized that it's easier to detect exoplanets that have period that is less than half of the observing period. For instance, all of the one on the bottom left, for instance, where you can clearly distinguish there is a difference between two-body template and third-body template. The same plot, but this is for the sky localization plane. So you have beta and gamma. And again, you see that you might have, of course, as a function of the signal to noise of the double white dwarfs and the mass of the exoplanet, you will see that you might have undetectable systems where you cannot really distinguish between two-body and third-body templates, and other ones that are detectable on the bottom row. These are the results for the exoplanets on the left. for which you have, again, where it shows much more clearly that it's easier to detect exoplanets that have periods that are much less than the observing period, well, observing mission time. So you have some detectable ones and marginally detectable ones. On a qualitative level, we found the same results as with the information matrix, the previous analysis, for which we can find exoplanets or third body that are around higher frequency double white dwarfs with a larger signal to noise. The exact number, this is something that is like in process at the moment. And on the left, you have the histogram of the brown dwarfs. We managed to do histograms because like you have many more detections, so it looks better. So where you have the injected population, so masses, period, and eccentricity from the top to the bottom, and the one that we are able to retrieve in blue. Okay, but what is the astrophysical context? Like you might ask yourself, like, okay, fine, you can detect exoplanets, but like, you know, the star is exploding, everything is going to chaos. Do these exoplanets for real exist? The answer is yes, and I'll try to convince you about that, like just showing some results from the literature. First, we know 6 exoplanetary systems that are circumbinary, for which one of the stars is a white dwarf. These are all listed here, and then we see that like the minimal separation is like 2.8 AU. For example, for UZ for NASA is the planet C. So this is like something that is within the LISA's detection limit. Obviously, we'll need like a second evolution, well, the second star evolving to become a double white dwarf system, and then we will have to check if the planets survive. But in theory, these exoplanets exist. So a work by Kostov et al. 2016, he evolved. I think it was 10 or 15. I don't remember the number exactly, but it was like all circumbinary exoplanets detected with Kepler. And he found out like that under specific scenarios, and I'm talking about scenarios because of course, like the evolution of compact binary stars is very complex. You might have that a planet survive and then becomes a bound planet around the double white dwarfs. That was done in 2016 with real exoplanets, and then like Colomba, Gabriele made a population study that I will mention later. For such, we know that these exoplanets indeed exist. Third, I already mentioned, like the compact binaries evolution is very different from the single star evolution. For such, given that they are compact, the star is not able to expand as much as in the single star case. And allow me to say that basically the planet as is like orbiting around the system is more protected than in a single star case. So here is the type of evolution for compact binaries. This is just a general case. So you start with the main sequence binary, then one evolved to main sequence, then you have an unstable mass transfer. For such, you have a common envelope. Then you have the ejection of the common envelope, and the result is a white dwarf plus a main sequence star. So if we carry on through the left, you have that the second star is evolving, then you have another common envelope phase, another ejection, and in that case, you have a double white dwarf. So you have to imagine that there's an exoplanet around these binaries, and these exoplanets somehow would need to survive to become like a bound exoplanet around the double white dwarf. But you know, common envelope is basically one of the most important problems in stellar physics. So there are many factors that need to be taken into account because we don't know many of the processes that are going on, and this can affect obviously the outcome of planetary evolution, because you might have ejection, or you have engulfment, or changing the dynamical properties of the exoplanet orbit. Another observational evidence that we have that this type of that exoplanets can survive the star evolution is indeed white dwarf pollution. So at the moment, there have been like many surveys about hot white dwarfs, and they found that these white dwarfs, the atmosphere is metal polluted, and the percentage goes around like 25 to 50%. When I say polluted, it means that they detect metals in the atmosphere, but that shouldn't happen because the gravity is so high that like this kind of metal should just like sink down and not be detectable, but we detect it. So there are different scenarios that have been studied in the literature, but the most trusted one at the moment is the fact that there is an exoplanet on a wide orbit that is acting as a slingshot for all of the debris disks. So basically, the debris is orbiting the exoplanets, and automatically they get thrown on the white dwarf. For such, it gets polluted because debris are usually rock debris and like remnant of planetary material. One of the examples is in this way they detected an exoplanet by Gajnik et al. 2019. Again, like 2 other planetesimal have been found orbiting single white dwarfs, and that might be indeed like an inference that exoplanet got destroyed, and then you have a planetesimal that is orbiting, or also the other case that you have. No, that's more for. That's more for the binary case, but like you might have like the debris of an original exoplanet. Just in 2020, we found our first giant planet candidate. I'm saying candidate because the mass is not very well constrained. And then in 2021, with my collaborator, we detected a giant planet orbiting a white dwarf in a wide orbit. This is a system that basically is the glimpse of it gives us a glimpse of the future of the solar system, because it's like the evolution of Jupiter around the sun. Right, so that was a global literature overview, but I tried to put in a scheme what we know and what we don't know up till now for circumbinary systems. So unfortunately, my mouse is not like, the cursor is not visible, but like let's focus on the infographic I put on the right, where you start with 2 stars and then instance like three planets. Then you have the first common envelope. With the first common envelope, you might have planetary ejection, because you don't know, like it depends by the architecture of the planetary system. But then you might have also planets that survive, but we don't know what is the surviving rate. And then you also can have tidal disruption events. So the exoplanet that's the closest one can get destroyed, and then it can form disks. So you might have a case where you have one white dwarf, one main sequence, and then you have the 2 original surviving exoplanets, so the 2 brown dots. But then you might have a second generation formation because you have a disk. So you have, it has been tested, and like it's in the literature that like planets can form out of the common envelope ejecta. So you might have a combination of the stellar ejecta together with the planetary debris, and from there you might have a formation of a second generation exoplanet. So you have, again, 2 stars, and then you have 3 planets, for which 2 of first generation and 1 of second generation. But then the second star goes through evolution, so you have a second common envelope, and it's exactly the same. You don't know how many planets can be ejected, you don't know the surviving rates, and again, you might have, again, formation. So this is a part of the HR diagram about planetary system that we really don't know much. And within LISA, we are trying indeed to solve and like develop this science case, for which in the end, you might have 2 white dwarfs, and then one first generation exoplanet, one second generation exoplanet, and then a hybrid or third generation exoplanet. Okay, so indeed, having this in mind, we said like, okay, let's just put it down. Let's try to evolve to do a population study of circumbinary system from main sequence until white dwarfs with 1 planet. And so Gabriele developed TRES, which is a numerical code for hierarchical triples, combining secular orbital evolution and stellar evolution, and interaction via heuristic recipe. So he made evolve a population of 10,500 exoplanets from the main sequence until the white dwarf stage. We did that to bypass the current lack of observational data and also to set up theoretical models for the future surveys. This TRES was already existing, but it was just made for stellar bodies. So it was a triple, a code for stellar triples. So we had to implement a lot of planetary feature, such as the one you can see listed here. We accounted for photoevaporation. We accounted for obviously the circumbinary stability criterion, and also rotational velocity. And on the stellar side, what we really updated versus the previous version of TESS, it was indeed the improved estimate of the gyration radius and the apsidal motion constant, because previously they were kind of flat as a function of the stellar phase, and now they change in a more detailed way. Okay, so how did we start our population? We used the same prior. We developed 2 populations. We had the same prior for the inner binaries. And these priors, I want to mention, that are the ones that have been used in the LISA data challenge for simulating the population of the LISA data challenge. And they are the ones that most, for which the simulation most match the observations. So you see the prior for the primary stars, secondary stars, and then the separation of the binary and the centricity of the binary. And we kept obviously the gamma and alpha parameters of the common envelope model to the one you see there, because those are the ones that are causing most of the changes. But like, given that they match the observed population, we kept those ones. Our goal was to understand, like, if depending by a different prior for the planets, we would have different results. So we developed 2 different populations. One was population A, that is based on observational data. The statistic of circumbinary exoplanets, even around main sequence stars, it's very little. So we have the numbers are not that much to be able to constrain these priors very well. So we use the single planet priors. You have well, the mass of the planet, the same major axis, and the eccentricity. And then for conservative reason, we just said, like, okay, let's go everything flat, and we did the population B to see like what was the result. We only simulate circumbinary giant planets because LISA will only be able to detect giant planets. So we just focus on that population. Okay, so you see here up on the right, the results of our population A and population B. And it was very, very nice when we saw these numbers. Basically, the Magrathea exoplanets, which are the ones that survive, we have that 23%, between 23 and 32% of these exoplanets survived evolution. Then we have the collided, which are the ones that whose orbit is intersecting the binary's orbit. Then we have the destabilized systems, which accounts also for the ejected one, because the simulation stops in the moment that the system is not anymore stable. And then the merged one are those for which the binary is merging. So you might end up having, catastrophic events, but also maybe one single white dwarf with an exoplanet. And then other categories that are less relevant to this presentation. But you see in these histograms on the left, you have the population A. In blue, it's always about the exoplanets. So you see that we only set exoplanets that were maximum distance of 200 AU. You see that you have an adiabatic expansion of the orbit of the separation of the planetary system. And this is absolutely, it was foreseen because of the adiabatic wind. So we know more or less that an exoplanet's orbit can expand 4 times the initial orbit. On the right, you have the eccentricity, and here what I want you to see, to focus more, is the change in the final eccentricity of the stars, for which you have a pileup at 0, because we know that most of the compact binaries, especially the one Lisa will see, they will just circularize and be having eccentricity equal to 0. And the other important thing is, like in both cases, population A and population B, we realized that the exoplanets that survive are orbiting stars that have masses that are less than 5 solar masses, which is not the case for all of the other categories, such as collided or destabilized. So the trends are the same as for both population, apart from the eccentricity, because on the right, if you start flat, you stay flat. But otherwise, more or less, the trends are the same. It gets different with the collided. For instance, you see that the final eccentricity of the external body is up to from 0.6 until 1, so it's literally crashing. And then you have the distribution of the merged, for which you might notice that the stellar masses, they go up, they cover up the whole range we simulated up to 10 solar masses. For such, like we started having like some more information about the parameter space that a circumbinary system needs to have for the planet to survive. Another result was the fact that here just all of the plots are for population A. The Magrathea exoplanets, they tend to like more a prograde inclination. So you have that the injection of the Magrathea's progenitor was absolutely uniform. And then like the results, we see that we prefer like this kind of system prefer like a prograde orbit. I included the cumulative distribution just to give you an idea more or less of how they change the category for both, so you can compare with the colors both planet population A and population B. But like what I want you to pay attention more is about the evolutionary stage in which things happen. Obviously, you can have ejection, engulfment, and collision whenever, like throughout the binary evolution. So we did a test to see where the star were, like the events were happening the most. So in the case of merged, where the stars merged, you have that most of the events happen in the post-main sequence. While for the collided events, we have basically everything in the main sequence phase, where the planet, like the orbit of the planet intersected the orbit of the binary. And then again, for destabilized, everything is happening mostly in the main sequence, range phase of the stars, both for primary and secondary, which is the two different colors. Okay, so you have the picture. Planets can survive and can become planets around double white dwarfs. But there are things happening in the middle because as I mentioned before, you might have that the ejection from the stellar ejecta from the common envelope, we know that 10% of the mass will stay bound to the inner binary and will form a disk. From this disk, you might have formation of second generation exoplanets. So we have the first generation that are the ones that form in the pre-main sequence stage. And then we have second generation. How did we come up with the idea of second generation? Well, because in the discovery of the enhanced Serpentis system, where we have two planets, 2 or 3, I don't remember, they found some, it was dynamically weird. They couldn't understand how it could be stable, where you have one white dwarf and one main sequence star. So they theorized that these exoplanets were formed later on, and the white dwarf has the age of 1 mega year. That means that if it's second generation planet, then it will be like the youngest planet we have ever discovered up till now. And that could help us, by studying this kind of system, that could help us to constrain information process and migration. But the question is like, okay, how do they form? Do they form from where? From the debris of the destroyed exoplanets or from the stellar ejecta? Obviously, the answer is we tested like the common level of stellar ejecta, and we know that it's possible, but it will not ever be so easy, like because you have a combination of different things. So this is just a first approach. So when you have the first white dwarf forming, so at very high temperature, 30,000 is the X where I put the first X on the HR diagram, you might have a first circumbinary disk created from the common envelope ejecta, from which a planet can form. But then you have, again, a second event where you have the secondary star that is evolving. For such, you might have a third generation if an exoplanet form from this other disk. And what is very interesting is that, like, obviously, in the whole chemical evolution of the star gets enriched. So it gets more metal, but it also can get more metal for all of the planets that is engulfing. For such, the protoplanetary disk will be much richer, and the timescale for forming exoplanets will be much quicker. And then you might have a hybrid generation where you have that one exoplanet got kind of destroyed somehow in the first evolution, but then in the second evolution, it's basically accreting on the stellar material. So you might have like an inner nucleus of first generation and then an outside nucleus of the second generation or third. No one ever tested up till this year. No one ever tested if you could form exoplanets around the double white dwarf. So Schleicher and Dreisler, their work is very famous because they analyze indeed trying to understand the enhanced Serpentis system. They analyzed the system where you have one main sequence and one double white dwarf, but no one ever realized we can form exoplanets around double white dwarfs. So a master's student of mine last year started working on this. So we used 4 systems that were the output of a stellar evolution code, which is called SIBA. It's a binary population synthesis code. And then by using the assumption that 10% can stay of the mass can stay bound to the inner binary, he tested whether evolution could happen. We don't have many constraints about the radial expansion of one disk, so he tested 3 different scenarios: 50 AU, 100 AU, and 150 AU. The larger you go, the cooler you get, and then obviously you can have it can be easier to form exoplanets in terms of giants. He tested different timescales. Initial formation time as a function of when the binary formed, the double white dwarf formed. So the 0 times T0, 0 years is exactly when the second binary forms. He tested what we could have. When the second binary forms, of course, the temperature, the effective temperature is much higher. So that's all obviously something that's affecting your disk. And then he tested also the case where you have a later formation for which the secondary white dwarf will be cooler, and also 1 mega year, which will be even cooler. The result, very, very simple, is that we always have terrestrial formation. Giant formation is it depends by the initial seed you put inside the disk. So you might have, when you start formation, exactly when the binary forms, you might have a formation of the giants when you start with lunar mass bodies, and when you start later the formation, then you need super Earth or mini Neptune as an initial body. And what we saw from the study, which was very reassuring, is that if they form through the formation migration process, they will indeed be found exactly in the LISA range, for which we will be able to detect it with LISA. With this analysis, indeed, we found no exoplanets within 8 years. So, but obviously this is just a first approximation, in the sense that you cannot just account a simple evolution. You have to have debris, you have to have a more specific simulation that at the moment are quite, well, the problem is complex. But if we have a combination of first generation and then second generation, these exoplanets that are first generation can also migrate towards a star. But that's something that will have to be studied later on. And finally, we, as a result of these systems, that like these exoplanets that were formed, another student simulated the stability of the system. She only analyzed, Ariana only analyzed 2 systems, and the range of the masses for these 2 systems were between 40 and 400 and 4,000 Earth masses for the first system, and then the second system between 50 and 1,500. The maximum orbital separation was 8 years, because it's the extended mission of LISA. And then she evolved all of this system to try and understand what was happening to them. So on the right, you see one of the results where you have the initial semi-major axis is the dot that is not filled, and the final major axis is the dot that is filled. For instance, for system number 20, you see that the binary had 3 planets, and then they didn't change much. Had 4 planets indeed, and then only 3 survived, and that's the result of the semi-major axis. Another case is, for instance, the green box, where you have the planetary system with the higher multiplicity. You had 4 planets, but then only 2 survive, and then you see that the field dots are indeed the ones the separation that they have with the main stars, with the main binary. Okay, so I think I convinced you to say that this is a very complex problem, because there are many astrophysical factors that we need to account for. We have to better assess the capability of LISA to detect these exoplanets. We have to include, for instance, in the gravitational wave form, we have to include multi-planet system. Also, we have to include the Kozai-Lidov effect and tides. We need to study the accuracy and precision of eccentricity. We will do another dedicated study for the LMC population, because now a paper came out by Kai et al. 2023, where we have exactly the numbers and the kind of binaries, so we'll do that. But then we have to develop also planetary evolution theories, such as the second, third mixed generation, and then the possible pollution of double white dwarfs, as well as the one I explained before of single white dwarfs. and also combine I just said that, like, yes, combining the survivals with the new formation. And the last thing, it will be to explore the synergy with electromagnetic observation. We know which kind of parameters we can resolve, but then we have to do and develop like follow-up strategies, because as you saw, we can only characterize 3 planetary parameters. We will need electromagnetic observation to indeed pin down radius, mass, density, and system orbit architecture. So the real takeaway is that, like, Lisa will provide important information on the final phases of planet evolution on a galactic level. If they detect it, or even if they do not detect it, it will give constraints. And here I close. Thank you.
Thank you so much, Camilla. That was awesome talk and really, really cool work that you're doing. So we have time for some questions. So folks are welcome to use the reactions tool to raise your hand if you want to ask a question, or you can post it in chat and I can read it off. I have a few questions, but I'll start off with my first one. So just going back to when you're just talking about these binary white dwarfs to begin with, you mentioned, and this is also not my field at all, so I'm very ignorant of all this background. You say that over 90% or so of stars in our galaxy are white dwarfs or will be white dwarfs one day. What is the number of the binary white dwarfs? How big of a drop off is that in comparison?
I have no clear answers to that, because that's not clear. Actually, I forgot to update the slide. Apparently, it's like 98% of the single star will become white dwarf. But then you have to. We know that at least 50% of the stellar population is in binary or multi-body systems. So your numbers go up.
Mm-hmm. Awesome. Thank you. So there's a question in chat that's asking, what about EM observations from ZTF and similar? And then a follow-on, can eclipsing binary timing variations be used to infer the presence of a circumbinary planet?
Okay, so ZTF is fantastic because obviously it can study the binary very well. But for what we're seeing now, the planet is not that close, so it will not help that much. This is a study, it's kind of in process, but given that the sample, like you will need a very long baseline to be able, well, that's more on a case of transit time variation. Okay, fine, let me go back again. We tested the probability of transit of an exoplanet around double white dwarf, and it's very low. It's like, obviously it's lower as the furthest is the planet from the central binary, but we are talking about less than 1%. So finding a transit, it's kind of tough, especially because these stars are very small. So I don't have like a straight answer for ZTF. I know that it's something we have to study more in details, but my guess is that you will need a very long baseline. As for the transit timing variation question, yes, that could help. But what is funky enough is that like there are quite a few like discussions still on exoplanets that are orbiting a binary system where you have, for instance, an M Serpentis. That's the only one that is basically quite not questioned. But there are many people questioning the real nature of this, because you might get confused. The signal you can see from transit time variation, you might get confused with the Applegate mechanism, which in some cases has been proved correct that it was Applegate, but the other ones, there's still the polemic open. So I would say yes, but very carefully. I mean, you might have interpreted the signal in a different way.
Gotcha. Thank you. So another question I had is just about the dynamics that you can detect and also what it means for the system, the dynamics of the planet itself. So you talked about that the detectability goes up if you have a short in orbital period relative to your observational time. I was just wondering, kind of ignoring the observation time, is there any sensitivity to shorter period planets to begin with? Like, it doesn't make the signal just stronger in general? Or is it just related to like you need to be observing for longer if you want to detect a longer period exoplanet? If that makes sense.
Yeah, you have at least to resolve a couple of periods, otherwise it's not going to be possible. Yeah.
Okay.
You might have in a case where you have acceleration going on, but that's something we haven't tested like properly yet. So you might have that with the acceleration, when you have an eccentric orbit, you might be able to detect it even if it's not 2 periods. I don't know. I don't have the answer at the moment.
Gotcha. No, that makes total sense. There's another question in chat that says, is there a chance for extremely near to Earth brown or even red dwarf stars with Jupiter mass planets LISA could see? Or does the Roche lobe overflow really limit the ability to see these planets around non-degenerate stars, even down to 0.1 solar mass?
I don't understand what's the system. So the system, you have a brown dwarf and a planet?
Yeah.
Okay, no, you cannot detect it with gravitational waves because you need something that's producing gravitational waves. So you need an inner compact binary or something very, very heavy that is like producing gravitational waves. You might not, no, you cannot detect brown dwarfs and exoplanet. Well, you mean an exoplanet orbiting a brown dwarf or a red dwarf?
Yeah, I mean,
No.
the point is it's, yeah, so maybe you have 10 times less mass, but if it's, within like 10 parsecs instead of looking as far as you can, are there close systems that might be interesting if they happen to be by?
No, not with the sensitivity of LISA.
Camilla?
Also, I forgot to mention, there's not just LISA, but there's also Taji, which is like a space mission from China or Japan. I think is China, that will also do the same things. And they also tested like, and they can detect exoplanets, but yeah.
Camilla, can I ask a follow-up question on this?
Yeah, of course.
Yeah, so following up with Jake's question, there is a brown dwarf binary. It's called Lerman 16, 6.5 light years away. Would that be detectable within the LISA? Maybe the amplitude, but not sure about the frequency. What's the period? Okay, that's a good question.
It's a red dwarf.
It's a double white, not white dwarf, sorry, brown dwarf. And the orbital period is, I'm looking on the Wikipedia system, it's called Lerman 16, LUHMAN 16. And the period is, oh yeah, forget it. It's not in the frequency range. It's 27 years.
But again, like it's not. It will not produce enough signal in the gravitational wave to be detected. So you really need that double white dwarfs and yeah. So there's the possibility of being able to detect one exoplanet around one white dwarf by gravitational wave, but it's very small. It's very small, such a probability, because that would be not an indirect method. It would be both of them producing a gravitational wave, and that's very difficult because indeed it has to be massive and so on. So yeah, the most direct way is having 2 double white dwarfs and another object on the outside.
Awesome. Well, we are at our time. Is there one last question for Camilla? I think I want to squeeze one in of mine as the host's privilege here. So just building off of what you were just talking with Ravi and Jake about, what's the flip side of that for the future, looking to the future past LISA? So if you have a double white dwarf system, but you want to get detections of exoplanets smaller than Jupiter, what does the future look like with that? Is it going to be really, really hard? Basically
it's
impossible?
another large mission. If you want, like NASA can start planning that.
Great. All right. Well, I'll give that to Ravi as homework to get that funding. But awesome. Well, Camilla, thank you.
Like, I mean, like, not even for suggesting it, I'm definitely on board.
Awesome. Yeah, I guess my question is, is this a many orders of magnitude difficult problem to get down to even just like a Neptune size, let alone like a super Earth? Or is it something that's actually reasonable, just needs a bigger mission, or just kind of TBD at the moment?
It's TBD, but you really need a different frequency range.
Gotcha.
Yeah.
Great. Well, Camilla, thank you so much for this talk. All of your work is amazing and very clear, and it was awesome research. So thanks for coming out and talking with us.
It was
and
great.
Thanks for everyone for joining. Go ahead and end the meeting here. I hope everyone has a great rest of your day and week. Take care.
Bye. Have a nice day.
Bye.